Everyone, and in Zoom and in the room. So we're very lucky today to have Marta Reina-Campos to talk to us a little bit about tracing the structure of dark matter halos using globular cluster populations. So Marta did her PhD at the University of Heidelberg, and then she recently joined McMaster, I think last year, during the pandemic, to become a CITA National Fellow. So she's one of our own. And so, yeah, so we're very delighted to welcome you here in person to give a seminar. So take it away.
Yeah, well, thank you, Ted, for the introduction. I like the she's one of our own comment. So welcome, everyone. I'm really excited to be giving seminars in person again. Today, I want to talk about how we think we can trace the structure of dark matter halos using globular cluster populations. And in order to study this topic, I'll make use of a suite of simulations that come from the eMosaics project, where we are modeling the formation and evolution of stellar clusters alongside their host galaxies, as you can see in the movie that is playing in the background of this slide, which corresponds to the assembly of a Milky Way mass galaxy with the gray color bar corresponding to the gas density and all the colored dots being the stellar clusters that are forming and assembling over cosmic time. So the structure that I want to give for this talk is first, I'm going to talk about different strategies that we can follow when we're trying to understand how stellar clusters form and evolve and their relation with their galactic environment. And then I'll talk about how we can use globular cluster populations and their host galactic environments, to link with their host galactic environments using spatial information. But first, I'd like to start with this slide that contains a quote from one of the first catalogs that observed stellar clusters and planetary nebulae in the Milky Way, which was done by Sir William Herschel and his sister. And what they write in their catalog is that, but first of all, it will be necessary to explain what is our idea of a cluster of stars, and by what means we have obtained it. For an instance, I shall take the phenomenon which presents itself in many clusters. It is that of a number of lucid spots of equal luster scattered over a circular space in such a manner as to appear gradually more compressed towards the middle, and which compression in the clusters to which I allude is generally carried so far as by imperceptible degrees to end in a luminous center of a resolvable blaze of light. We now know that the objects that they were observing in the Milky Way correspond to gravitationally bound stellar systems that are as old as the universe, that tend to have low abundances of iron, so they're metal poor, and that they're extremely massive. So these objects have between 10 to the 5, 10 to the 6 solar masses. And these are extremely beautiful objects. As you can see in these figures, they tend to have a sort of circular shape, and that's why they were called globular. If we look at the population of these objects in our own galaxy, this is a very cool image from the Gaia satellite. This figure is representing the stellar density map from the early data release 3 of Gaia. And each pixel in this image corresponds to the number of stars per unit area covered by the pixel. And so brighter pixels correspond to more stars in the galaxy. As you can see, we can very clearly see the feature of the galactic disk with the dust clouds and the small and the large Magellanic clouds. And for the people who are in Zoom, might be easier. For us, it's a bit more difficult. But if you have a screen with a bright display, you will see that there's some very bright spots that are sort of scattered around the galaxy. And if we identify what these objects are, the vast majority of them are globular clusters. Yeah, thank you, Neil. Yeah, okay, this helps a bit. So for example, this one, it's a globular, these ones are as well. And we now know that our galaxy contains between 150 to 200 globular clusters, or objects that are similar to the ones that Sir William Herschel and his sister were observing back in the 18th century. But this is not all that we see. Actually, if we broaden our definition of what stellar clusters are, we see that there's quite a variety. So this is a figure from a review by Mark Krumholtz and collaborators that I really like, because they're showcasing the wide range of properties that we see that stellar clusters can have in the Milky Way, as well as in the small and the large Magellanic clouds. This figure is showing different stellar clusters that are ordered by the age. And we're seeing that there is a stellar cluster formation happening currently in the Orion Nebulae. Some clusters have a few mega years old, some of them are a few hundreds, a few giga years, and some objects, the most extreme ones, are a few giga years old. What's also interesting from this figure is that these objects are also showing a range in their masses, going from like a few hundred to 10 to the 6 solar masses, as well as differences in the abundance of iron and other chemical elements. What we're now trying to do is to understand stellar cluster populations as a continuum, whose physical properties have been shaped by where these clusters form and how they have evolved over cosmic time. And so under this idea, the objects that were first observed by Sir William Herschel would be these massive, would correspond to the massive old metal poor end of this continuum distribution. But what this idea or this hypothesis suggests is that if the right gas conditions for cluster formation are met, we should be seeing massive cluster formation in the local universe. And indeed, this is what we see when we look around in the local universe with telescopes like the Hubble, and we are observing particularly high pressure starbursting dwarf galaxies like in the Untitled Galaxy. This is where these objects were first observed, but we're seeing similar type of massive cluster formation, not just in the Untitled, but almost in any other starbursting galaxy that we're looking at. And these objects, which in this image would be these compact blue dots, we're now referring to them as young massive clusters as a contraposition to the old globular clusters that were first observed in our own galaxy. And so we can now say, well, maybe under this hypothesis that stellar clusters are part of a continuum, maybe these objects are not so different. And if we look at certain properties for young massive cluster populations and globular clusters, this slide is just showing 3 examples for each of the 2 sort of categories of objects. We can see that actually they're fairly similar. These objects have similar masses, they have similar sizes, and both of them are tracing the stellar environment. What they differ in is that young massive clusters are currently forming, whereas globular clusters are seen to have between a few gigayears to ages comparable to the age of the universe, and the fact that they're sitting in different environments, because young massive clusters are generally still embedded within their gas-rich natal environment, whereas globular clusters tend to be sitting in much more gas-poor environments in the outskirts of galaxies. And so this leads to the natural question of considering, well, maybe are the ones that formed at early cosmic times and that have managed to survive to the present day so that we can observe them. And these are just the ones that are forming, and not all of the young massive clusters will survive 14 gigayears of evolution into the future to be observed as globular clusters. So with this idea of whether globulars are the products of regular cluster formation at high redshift, this is our current understanding of how stellar cluster formation evolution happens. Once upon a time, when the universe was young, galaxies were extremely gas-rich. And in these gas-rich galaxies, there were clouds of gas that would collapse and lead to the formation of massive stellar clusters. And the combined effect from the stellar feedback from these massive stellar clusters, together with the high merger rates that galaxies experience at those early cosmic times, will help stellar clusters to migrate from their natal environments towards the outskirts of galaxies. And this is a crucial step because the stellar clusters are going to lose a lot of mass if they remain within these natal gas-rich environments, whereas once they move out, they're much more likely to survive to the present day, and so that we can observe them to be globular clusters. But what this is telling us is that if we really want to model how stellar cluster formation and evolution occurs over 14 gigayears of evolution, we need to take into account that the galactic environment is also evolving. And actually, that the galactic environment is embedded within a larger scale cosmic web. And so we need to be able to model from the starbursting environments where we see massive cluster formation in the present day to the more quiescent galactic environments where we see evolved globular cluster populations, all while keeping in mind that these galaxies are embedded within a large scale structure. So this leads me to the first bit of my talk, where I wanted to discuss, well, how can we do this? Which sort of strategies can we follow if we want to study this from a theoretical perspective? The way I see it is that the tool that you're going to use depends on the question that you're trying to address. And so if we start focusing on the small scales, one can say, well, actually, I don't really care about the galaxy. I just really want to study how star formation happens. And so we can just look at one cloud within the galaxy. And in order to do this type of simulations, we can try and address the question of how do individual star clusters form from collapsing clouds. To do this type of simulations, we typically have one collapsing cloud in a box. This cloud is collapsing, is turbulent, is collapsing, and then there's some star formation happening. The stars within the cloud will produce stellar feedback, and so the cloud will disappear. But what happens when you get rid of the gas? This stellar cluster is going to be gravitationally bound. Is it going to survive for 14 gigayears of evolution? Well, that's another question that we might want to address. How do individual star clusters evolve in a galactic potential? These sort of simulations only require evolving the embodied part. So just gravity, not hydro anymore, but it's still one cluster within a box. And so in these individual cluster simulations, as I call them, they are extremely nice from a resolution perspective, or extremely computationally expensive, depending on how you want to look at it, because one star in these simulations typically corresponds to an actual star in the universe. The time scale over which one can run these simulations is slightly different. Collapsing clouds, it's only required to run for a few mega years, because once you have stellar feedback and you don't have gas, you don't really care. However, for the evolution of clusters, we need to be able to model them for several gigayears. We can run several or a large number of models for each of these two types of simulations, but the caveat that they have is that they do not include the galactic environment or the cosmic evolution. These are just a couple of examples of very recent works. There's a very large community working on this aspect. And as you can see, for example, this is just a turbulent cloud collapsing in a box. You can see how it has formed some stellar clusters, and the stellar feedback from the clusters is disrupting the cloud and so clearing out the natal environment. So these are very exciting works, but as I say, they do not include the galaxy. So what can we learn from these type of simulations? Well, we can look at intrinsic cluster properties. We can look at the detailed chemical abundances that these stellar clusters are going to have. We can look at what the role of a specific feedback mechanisms. We can look at the formation and evolution of binaries in these systems. And we can also even look at what the formation and evolution of exotic stellar species. And this is really interesting because we can compare each of these type of predictions with either current or upcoming observational facilities. So that's the first scale. Now we can say, well, actually, maybe one cloud is too limiting. I actually want to include the galactic environment in my simulation. So the next question we might want to address is how do star clusters form and evolve within a galactic environment? These simulations are these are the state of the art. They're really nice because what they do is that they are pushing the resolution of the simulation. So it's that one star in this simulation is actually one star in the universe, or at least a low mass population, so a few hundred or few thousand solar masses. As I say, they have extremely high resolution, which means they have extremely high computational cost. So the time scale over which these simulations can be run is extremely short, for a few hundred mega years to a few giga years. You can run a small number of models, but at the same time, you are including the galactic environment with extreme detail. So that makes them very exciting, but they don't have the cosmic evolution. So again, these are just a few examples. This is a very active field of research, and these two groups have actually published papers within the past couple of months that are very interesting. But you can see that the resolution required to actually resolve the stars within the cluster and at the same time be able to model the entire galaxy is extremely challenging from a computational perspective. So what can we learn from these type of simulations? Well, we can still look at intrinsic cluster properties. We can still look at detailed chemical abundances. It's a bit challenging, but we can still look at how binary systems form in these type of environments. And we can look at what's the role of the galactic environment. So for example, what's the role of galactic mergers in influencing how stellar clusters form? The last step of my scale of questions is to say, well, I want to have a galaxy, but I also want to be able to describe its evolution over a Hubble time. So the next question you might want to address is how do star clusters form and evolve within a cosmological environment? And in order to address this question, we need to sacrifice something. I just said that if we want to be able to resolve the stars within the clusters, that's extremely computationally expensive, so we cannot run for a long time. So what we sacrifice in these sort of simulations is the resolution. What we're doing is that now one star in our simulation corresponds to an entire cluster population. And so clusters are subgrid within the simulation. We do not have individual particles for our clusters. They're just properties that are tagged along our star. But although we are sacrificing on the resolution, we're gaining on our ability to run the simulations. And so we can run for 14 gigayears of evolution. We can run a large number of models, and we can consider what's the influence of the galactic environment and this cosmic evolution. There are two main projects that are trying to address this question. Oh, you're welcome. Can you hear us? Okay, perfect. Yeah, thanks so much. So as I was saying, the main difference between these two projects is that in the EMOSEX project, we have a description for the interstellar medium that is basically a warm phase. Whereas in the EMP Pathfinder simulations, we have made an effort at trying to model the multi-phase nature of the IATM so that we have a description for the cold phase. I'm not going to talk about Pathfinder today, but if you're happy, I can answer any questions. So what can we learn from this type of simulations? Well, because we have sacrificed on the resolution, our clusters, they don't have resolved stars. They're not even a particle. They're just properties tacked along to the stars. We cannot do any predictions on intrinsic cluster properties. But we can make predictions on cluster formation at high redshift. We can look at where are the relics from cluster disruption in phase space. We can look at the influence of the galactic environment on cluster demographics. And what I'm going to be talking about today is we can try and use evolved stellar cluster populations to link them with how their host galaxy has formed and has assembled, or what is their host galactic environment at redshift 0. So this leads me to the second part of my talk, which is how we can use these evolved stellar cluster populations to link them with their host galactic environment. And in particular, I'm going to focus only on using spatial information. So we take a picture of a galaxy, we look at where clusters are, and that's all the information that we have. So as I said, these are some results that I have obtained from the EMOSEX project. EMOSEX combines a subgrid description for stellar cluster formation and evolution within the Eagle galaxy formation model. And combining these two descriptions allows us to describe from the large scale structure down to one node within the cosmic web, one galaxy, and the stellar cluster population within this galaxy. Within this project, we first run a complete volume limited sample of 25 cosmological zoom-in simulations, but we have also run a periodic volume that has 34 megaparsecs on the side. And that's what I'm going to be showing, the results of which I'm going to be showing today. So the first question that I would like to explore today is, can we trace the origin of globular clusters using their radial distributions and metallicities? And the reasoning behind this question is that when we look at the globular cluster population in the Milky Way, we see that it has a bimodal metallicity distribution with a peak center towards low metallicities and another one at high metallicities. And we see that the more metal poor objects tend to be in farther out distances. And so if we look at the number density radial profile as a function of galactocentric radii, as in this figure, what we see is that the metal poor globular clusters tend to be much farther out than the metal rich ones. And there's this idea that these must indicate that most of the metal poor globular clusters have an accreted origin, whereas the metal rich have a preferential in situ origin. So this is a question that I'm trying to address. The first thing that I'm looking at is I'm taking the all the galaxies within the 34 megaparsec periodic volume. And the first thing that I'm looking at is I need a way of making sure that the spatial distributions of globular clusters that I'm going to be using for my analysis make sense. Because if it doesn't make sense, then there's no way that I can get any sensible conclusions out of them. So the way to checking that they make sense is to quantify the projected radial profiles. I project my galaxies, I calculate what the radial profiles, and then I see different functional forms that give me an idea of what these spatial distributions look like. The first functional form that I fit for is just a power law function, and I'm fitting for the power law slope. And the second one is what we call a de Vaucoulet profile, which is a Sersic profile that has a fixed slope of n equal 4. And so we're just fitting for the effective radial. And the combination of the power law slope and the de Vaucoulet effective radii gives us an idea of whether the distribution is more shallower or steeper and much or less extended. And so I'm going to be showing these two parameters as a function of the galaxy stellar mass of the central galaxy. So when I quantify the radial profiles for my entire globular cluster populations, which are shown here in black, but also if I split them by metallicity, so blue dots correspond to metal poor globular cluster populations and red dots to metal rich ones, I'm seeing two trends. The first one is that globular cluster populations that are hosted in more massive galaxies show shallower because we see that the slope decreases and more extended radial profiles. These are the kind of overall trend. But when we focus on a given galaxy mass, we always see that metal poor globular clusters tend to be shallower and more extended. And these are the exact same observational trends that we have been seeing in galaxies around us, as well as in the Milky Way. Just as a note, the purple star here is the Milky Way. So you can see that our simulated populations actually make sense with what we have in the local universe. So this is like a green tick. We can go forward. The next thing we can look at is actually look at what are the radial profiles of the different populations that have formed either in situ or accreted. This is a very overwhelming figure, so let me just walk you through it. What we're looking at is the median radial profiles of globular cluster systems in the vertical axis as a function of the galactocentric radii normalized by the stellar half-mass radii of each galaxy so that we can compare galaxies of different masses. Then, as we go from the left column towards the rightmost column, we're looking at globular cluster populations that are hosted in more massive galaxies in 3 different mass bands. And as we move from the top of the figure to the bottom of the figure, we're looking at globular cluster populations that have our fiducial metallicity range, or we're just focusing on metal poor objects, or we're just focusing on the metal rich ones. And last, we can divide each globular cluster sample by whether it has formed in situ or it has formed in a satellite galaxy that has been accreted later on time. So if we start looking just at the first row, what happens with the fiducial globular clusters? What we're seeing is that as we go towards the right side of this figure, more massive galaxies contain a larger fraction of accreted globulars, because as you can see, the green line is taking over the orange as we go towards the right. This goes in agreement with what we know from galaxy formation, that more massive galaxies have larger fractions of accreted stars. So this is also is consistent with our previous knowledge. As we explore the globular cluster populations that have different metallicities, we see that in the low mass regime, so these are galaxies that have low masses, we do see a big difference between the radial profile of metal-poor globulars and metal-rich ones. While metal-rich globular clusters are mostly in situ, metal-poor globular clusters tend to have a mixture between in situ objects and also accreted ones. And it is the presence of the accreted objects that's extending the radial profile towards the outskirts of galaxies. What I found quite interesting was that when we extended these analyses for the most massive galaxies, we found that actually the accreted globular clusters are always dominating your sample. And so it doesn't matter what's the metallicity of your object. If you're looking at a massive galaxy, because these mostly build due to the accretion of satellite galaxies, you're quite likely just looking at an accreted object, regardless of the metallicity. So this was an exciting conclusion from this first project that led me to the second project that I want to present. This has been a fun little summer project that has grown into a monster of several heads. So just let's see if I can get it straight. So the original idea for this project comes from this paper by Mireia Montes and Ignacio Trujillo from 2019. The authors used deep observations from the Hubble Frontiers field of galaxy clusters to look at the intra-cluster light. So this is the diffuse stellar light that is between galaxies in a galaxy cluster, and that is thought to build from the accretion of satellite galaxies. And what they do is that they use these observations of the intracluster light and they compare it with what is the structure that you see in those observations compared to the structure that you get from mass distributions that come from weak lensing and the distribution that you see in X-ray observations. The idea is that generally X-ray observations are a good tracer for the matter distribution in galaxy clusters, but actually what they found is that the diffuse stellar light components seem to be a better tracer for the overall mass distribution than what X-rays was giving them. So what this gave us the idea that if you can do that with stars, maybe you can do it with globulars as well. So this is what I've been working on sort of since June or so. What I'm doing is that I'm taking all the galaxies or all the halos within the 34 megaparsec periodic volume, and I'm trying to replicate what observers would be able to see from them. So I'm looking at, first of all, I'm looking at the dark matter distribution. So these are dark matter surface density images for one of my halos. This is the most massive one. And this is the original matter distribution that we're gonna see if we're capable of tracing. Then I'm taking the stellar populations within this halo, and I'm using their physical properties to calculate their magnitudes in different filters. And in particular, I'm calculating what's the stellar surface brightness image for the SDSS R band, because we see that the intracluster light is more prominent in red bands. And this gives me an image similar to what observers would be able to see. And at the same time, I'm selecting the globular clusters within this halo with observational cuts that resemble what it is typically done in surveys. So I'm selecting globular clusters to be brighter than the peak of the globular cluster mass function and to have certain color combinations so that they are old and massive, basically. So with these three images, the question that I'm going to try and see is, are there structures or shapes in the stellar or the globular cluster density image that resemble what we see in the dark matter distribution? And so the way, this is very exciting, by the way, because deep observations of stellar components, as well as a lot of spatial distributions of globular clusters, are soon going to become available as all of these surveys become online. So how do we identify these structures? The way we're doing is that we're taking each image, we're binning it in radial profiles, and we're calculating what's the average density in each of these bins, and that is giving us a surface density radial profile. Once we have this radial profile, we say, well, we want to look at the structures at different scales, and those are these vertical lines. In particular, here we're using 7 different radial scales that go from 1% to 7% are interpolate the value at this radial distance. And then we go to matplotlib contour and we say, please draw me a line that joins all the pixels that has this density value. And then you get this isodensity structures overlaid on top of the image. This is quite interesting. The problem is that, as you can see in the image on the right, this is extremely noisy. So this is very difficult. It is quite difficult to study any type of structure from here. So the first thing that we need to do is smoother images with a Gaussian kernel. And in particular, we've decided to use a size of the kernel that is about 2% R200. And the reason for this is that the effective radius of the galaxy is about 1.5 R200. So we're smoothing over scales of the central galaxy such that we can get rid of all the small scale noise while still retaining the signal that's coming from the substructure. And so what we're looking at here now is the stellar surface brightness map, the dark matter surface density, and the globular cluster number density images that have been smoothed, and then with all the isodensity contours identified at different radial distances drawn on top of it. And you can see already by eye that in this particular halo, we're identifying different structures. So if we were to look at the stellar surface brightness map, we see the central galaxy, but we also see the satellite. When we look at the globular clusters, we see the central galaxy, and then we see an envelope that is containing both the central and the satellite. Whereas in the dark matter, we see both the structures. So the question is, are they lookalikes? Can we actually use the stars and the globulars to trace dark matter? So the first way that I'm trying to assess this is, first of all, just putting everything within the same figure. This is a bit of a mess, so let's zoom in into the region of interest. What we're looking at are the isodensity contours identified in the dark matter and the total mass with these black lines. The isodensity contours from the stars are the orange, and then the ones from globulars are the red ones. And as you can see, in the stars, we're identifying the central galaxy, whereas the globulars is seeing the central galaxy as well as this envelope that's surrounding the satellite. Whereas if we just focus on where the matter is, then we're just seeing the satellite because it's such a dominant substructure presence in this particular halo. So this is just a qualitative description. We can do this for all of our halos, and we overall see that the stars and globulars trace dark matter. This is actually the one that doesn't work, so that's why I like to show it. But we can be a bit more quantitative, and actually we can quantify how similar these contours are. There's a metric from shape matching techniques that is called modified Hausdorff distance that quantifies what's the largest distances between a pair of contours. So in this case, when comparing the globular cluster and the dark matter, we see that it would be this distance here. So now what I'm going to do is that I'm calculating this modified Hausdorff distance between my pairs of observed tracers, so stars and globular clusters, against my pair of true tracers for the matter distribution, dark matter and total mass. And I'm doing this at 5% of R200. So here we're looking at the inner region of the dark matter halo. This is the quantity that I'm showing in the vertical axis normalized by R200 so that we can compare galaxies of different masses. And all of these distances are shown as a function of the galaxy stellar mass of the central galaxy within the halo. The first thing that we can see is that it doesn't matter whether we're comparing against the dark matter or the total mass distributions, the results are the same. This gray shaded region is telling us that the distance that you're measuring between the two contours is larger than the distance at which you're drawing the contour. And so what's happening quite likely is that one of the contours is seeing a structure at around 0, 0, and the other one is seeing a substructure or some subhalo around the halo, and that's why the distance is so large. So if anything is sitting in the gray shaded region, it's quite likely that it's the influence of substructure. And actually this data point here is the halo that I've been showing up until now. The other thing that we're seeing is that actually when we're looking at the globular cluster contours, they seem to be tracing the overall shape of the dark matter distribution a bit better than what stars do. And this is interesting because when we do the same analysis, not in the inner part of the dark matter halo, but at 20%, we actually see the opposite behavior. And my current interpretation is because stars, it's actually a diffuse continuum component, whereas globular clusters are just point tracers. So there's a moment in which you just don't have enough statistics to carry this analysis. The other, sorry.
Yeah, I just wanted to ask, is there?
Wait.
Oh, sorry.
No worries.
I just was curious if there's some property of this particular distance metric over the contours that is much better at tracing out sort of correlation and structure versus just doing like a dot product or in just computing correlation coefficients between these various densities.
I don't think it is. I think it's just simpler to calculate at least. So it would be interesting to look at these metrics now that you bring them up. I've been looking at this one because this is the one that the original paper uses. And so I wanted to be able to compare to the values that they get for their objects, but it would be interesting to look at what you measure actually. Yeah, thank you.
Thanks.
No worries. Yeah, so now that we sort of looked at how similar these contours are, something else that we can look with these distributions is try to quantify the morphology a bit more. So using these contours is not a standard technique within the community, but it's fairly common to look at for a given spatial distribution to calculate what's the moment of inertia tensor, and so get the eigenvalues and eigenvectors from this distribution. This is what I'm going to be doing now. This is the same halo that we've been looking up until now. This is the panel on the left is showing the projected particle distribution of dark matter, then stars and globular clusters. And I'm weighting the moment of inertia tensor by the mass of the particles. And it also has the title of reduced because we are weighting each particle by the inverse of their distance so that we reduce the influence of outliers that are sitting very far out. So when we calculate this mass moment of inertia tensor, we need to consider initial apertures at the beginning. And so I'm considering two. One that is at 5% R200 and the other one at 20% R200, so that we can study what's the morphology of these systems or of these distributions within the inner halo and sort of at the outer halo. And once we have the moment of inertia, we can calculate what are the eigenvalues and eigenvectors. But we can look then at the ellipticity of this distribution by looking at the ratio of the eigenvalues. And we can look at whether two spatial distributions are aligned or misaligned by looking at the angle between the semi-major axes, which are the major eigenvectors. So when we look at these quantities, when we start looking at the ellipticity, we see that especially in the inner part of the halo, our dark matter structures seem to be very circular, and then globular seems to be a bit more, and then the stars. I think this is fairly in agreement with what I would expect. So I'm not too surprised by this. And then the other quantity that we can look at is whether the spatial distributions are aligned or misaligned. And what we're seeing overall is that the two distributions that seem to be more aligned one to the other are stars to dark matter. And then globular clusters seem to be showing the same level of alignment with both dark matter and stars. So just to summarize, I think I'm one in time. So just to summarize, I've sort of been discussing different numerical algorithms that we can use to model the formation and evolution of stellar clusters at different scales, whether just focusing on the details of their formation and evolution to even considering 14 gigayears of evolution. I've shown that the radial profiles of globular cluster populations can encode information about their origin. And we have this tentative project that's suggesting that we can use just the projected number density distributions of globular clusters to trace what's the actual shape of the dark matter halo, which I think is quite cool, especially given the amount of data that we'll be able to use from now onwards. And that's me. Thank you.
Thank you very much, Marta. We have some questions, a question on Zoom from Bob, and then we'll take any in the room. So Bob, go ahead.
Hey there. So I guess I'm wondering what you define to be the center of the cluster when you're working out the moments, because some of them look kind of like train wrecks, but I thought your ellipse was sort of centered on the BCG. So what do you define the center as?
I'm just using a very theoretical definition, which is probably not the best, because I'm just using the particle with the lowest potential. So just the standard way of centering halos in simulations. But yeah, no, it's a good question, because especially for the shapes, observationally, sometimes it's confusing to know which galaxy is the VCG. So there might be ambiguity there. I'm using the central galaxy. So maybe that aspect could be improved within the current analysis.
Thank you.
Any questions in the room? Zoom? Chris, you've got your hand raised. Do you want to?
Hi, yeah. Can you say a little bit more broadly about what's being learned about the fate of these star clusters, how they're destroyed, how their distribution with respect to mass changes with time?
So sorry. So your question
In
is
these,
related to
in
how
these,
solar clusters lose mass in these simulations?
in the,
How
yes, yes, exactly, and how that depends on, I guess, position in the galaxy or the initial mass of the cluster.
Okay, so we consider that stellar clusters can lose mass through mainly four different processes. One is just stellar evolution. It's just considering that the stellar clusters are made of stars. The stars lose 40% of their mass due to evolution. So that's one component. The other one is dynamical friction, which we have to apply in post-processing. So in post-processing, we analyze all the snapshots and we say, given the position and the velocity of this stellar cluster within the host halo, the dynamical friction timescale, if that is smaller than its age, we consider that dynamical friction would drag in that cluster. We need to do that at post-processing because clusters are just tag along on our star particles, and so we cannot drag the entire star into the center at runtime because that would be wrong. So that's the second one. And then we consider dynamical processes. So we have quick variations of the gravitational potential, so tidal shocks. We have tidal shock disruption, and we have two-body interactions. So we have analytical prescriptions, especially for tidal shocks and two-body interactions, that basically depend on the density of the cluster and the strength of the tidal shock, or the strength of the tidal shock or of the overall tidal tensor. So we calculate at runtime what is the variation of the potential, so the tidal tensor. We calculate how that changes with time, and then with that we can apply the right amount of disruption. We see that because these disruption mechanisms depend on the density of the cluster, and the clusters have a fixed size, they basically depend on the mass. So lower mass clusters tend to disrupt more easily than higher mass clusters. That's true in e-mosaics. In Pathfinder, we're playing with those ideas, but that's the scenario for e-mosaics.
I mean, are these prescriptions being calibrated in some way using, say, zoom-in simulations?
No, they're calibrated with m-body simulations. So the analytical descriptions are calibrated with m-body simulations of how tidal shocks affect stellar clusters. And the same for the two-body interaction prescriptions.
Right. Okay, thanks.
No worries.
Okay, so I think we had Gwen, then Ting, and then Mike. So Gwen, go ahead.
Hi, Marta. Thanks for a really great talk. And really interesting results too. So I had a question about the step where you're doing the kernel density estimate of the 2D image, and you chose a bandwidth, and you chose like 0.2 times or 0.02 times the R200 value. And so I was just wondering, with the simulations, you know what that R200 value is, but with real data, it would be an estimate. And so I'm just wondering, like, how much uncertainty in R200 would put into this method of tracing the dark matter with the globular clusters?
I think it doesn't really matter what's the exact size of the kernel that you use. We quantify everything in terms of R200, because then we can extend the analysis for all the galaxies without really caring what's the mass of the galaxy. What I've seen, so I've been playing a bit with the value of this kernel. And what I'm seeing is that basically it needs to be sort of the order of the effective radii of the galaxy or larger, so that we can remove the small scale structure. But if you go too large, then you just end up with smoothing all the signal and you just have one blob in the image. So I have some, I think they're cool, but I have some figures where I'm just like showing different kernel applied to our data and the type of contours that you identify. And it's basically that you go from a lot of small scale noise to one blob. And then it's a matter of choosing which one looks better. I think for observations, we might not have this issue just because applying this kernel size would be resembling to like the beam size, sort of smoothing the resolution of your image. But that's
Okay, yeah, thank you.
perspective, so I don't know.
Yeah, and no, thank you so much, Marta.
Okay, Ting.
Yeah, very nice talk. So my question is about this final conclusion. So have you looked at the distribution, how it varies versus different metallicity of globular clusters, and see if this correlation is better for particular type of population of globular clusters or not?
No, I haven't. I haven't split, so I haven't done the analysis of these isodensity contours for different metallicities, but it's certainly something I could look into. It took me a while to play with the data to find the right way of selecting the globular clusters, because an issue we have in e-mosaics is that we do not disrupt clusters too efficiently. So there are clusters in the simulation that shouldn't be there. So how do you choose which ones those are, and how do you make sure that they don't end up contaminating your data is a bit of a challenge. And how you do that from an observational perspective, it's a bit more of a challenge when you're a theorist. But it's certainly, looking at the metallicity is something I can look at, certainly, yeah. So I'll let you know when I...
Yeah, but that's actually this another question I have is, so when you say it follows, it's more like I guess quantitatively, does it follows in terms of like one-to-one relation, or it's just proportional? I'm not sure if you see what I'm asking. I guess the other way to ask is how the treating of the disruption rate of the globular clusters could matter this result. I'm not sure if...
I mean, hopefully, if I've done a good selection of the data, it doesn't matter. But there's always that worry in all of the results from e-mosaics. So normally what we do is that we use, so we know that the safe population to look at are massive clusters and not too metal-rich ones. And if it's possible, also do a cutting edge. But almost none of those quantities are nice to do from an observational perspective. So I have some figure that I could show you later. I spent a while thinking how I could mimic those sort of physical cuts with observational quantities. So what I end up doing is that you can transform the peak of the globular cluster mass function for a cluster at 8 gigayears and solar metallicity into a magnitude, and then say, okay, I'm getting all clusters that are brighter than that magnitude. But once you get those clusters, because of this under disruption, we're seeing that there are too many low mass, metal rich, and young clusters. But then you can play the trick of doing color-color combinations in which one of your colors is a UV filter. And that way you can really discard the young clusters. And so you can make a selection in color-color space where one of them is a UV filter, and then you just get rid of the low mass, metal rich, and young clusters. So that took a while of playing with the data. But I'm quite happy with the selection now. So I could show you figures later if you want.
But I guess we should talk probably later, but I guess the question really is, how could you say the relation you are seeing now for the number density of globular cluster and the shape of dark matter is not an outcome of the way how you do the selection, or it's not a way how the simulation runs in terms of tidal disruption? If these numbers or changes, maybe I guess the conclusion could be a tunable of these two kind of parameters that result in this kind of correlation rather than an actual thing that happens in these things, right?
Yeah, absolutely. I think it's a perfectly valid concern with any of the results that we get of the simulation, like how certain are we that the selection we're doing is correct. I think the same could be said of the fact that these are subgrid models. So all of our analysis relies on the fact that the input models that we're putting in actually make sense, and that the redshift zero properties that we're getting actually make sense. So we're constantly trying to validate that the models that we have input into the simulation for the subgrid description are sensible with what we see in the local universe, and that the redshift zero properties are sensible. That's why, for example, in the first project that I was describing, I was making an emphasis of making sure that the spatial distributions are what we see in the local universe. I think overall, I'm not too concerned, but I'd be happy to discuss this further with you if you want.
Thanks.
No worries.
Okay, Mike.
I guess my question was very similar to that. I'm trying to think of a way to rephrase it in a different way. You know, you might expect that, you know, the accreted globulars are tidally stripped off of satellite as they fall in. And so they follow the orbital path of the infalling satellite. And then if that object is then accreted again into a larger object, those less bound globulars are more likely to strip off and orbit in the potential. So another way to think about it is maybe if you look at the number density of GCs divided by whether they were originally in, you know, accreted once, twice, you know, do they trace the dark matter more accurately?
I don't know because I haven't looked into it, but I guess it's something to consider as well. I just came up with another way of replying to Thing's question, and is the reason why we see that there's these under-disrupted stellar clusters in our simulations. It's because the Eagle galaxy formation model does not include a description for the cold phase of the ISM. So this under-disruption basically affects mostly to the clusters that spend more time orbiting in the galaxies. So it's not going to affect to the signal that we're getting from the outskirts. It's going to affect whatever we're getting from the galaxy. So that's why, kind of, if we're looking farther out from the galaxy, I think it's going to be fine, even though we still have some contaminants coming from the disk of galaxies. I don't know if this is addressing anyone's question.
That addresses both. Okay, Lee Chen, you're up with I guess maybe one of the final questions, because we've grilled Marta a lot. Go ahead.
I can try to be brief. Yes. Thanks, Marta. A very interesting talk. So, so you mentioned that actually the simulation actually is implemented with separate models for tidal stripping as well as a dynamical friction process. So I'm actually more interested in the survival, the chance of survival for the globular cluster. Is there any, for instance, observationally, there's like observational constraint of the age distribution of globular cluster, and then how does it compare to the simulation? Whether the simulation has reproduced the observed like age distribution as the observation?
Are we?
Yeah.
I might be
in other words, I'm interested in how much is the chance that a globular cluster is destroyed by the dynamical processes?
Okay, so I might answer not using results from eMosaics, but from Pathfinder instead. So the other suite of simulations that I've been working on, where we do have the cold phase of the ISM. And there, what we're seeing is that there's a lot of disruption. So if you have so if you're a cluster that have low masses, you're very likely to end up disrupted. I just finished the first draft of the reference paper of analysis, but I can already tell you that the number of the stellar clusters that you form versus the ones that they survive nowadays, there's probably at least 2 orders of magnitude difference. So there's a huge influence of the galactic environment at just disrupting these objects. Yeah.
Thanks. Yeah, I book a slot, so we're gonna discuss later.
Oh, we're Reiner's neighbor.
Yes.
Oh.
Yeah. It's me. Yeah.
I don't know who that is. Any questions in the room, Marta? All right. I think we'll give you another round of applause and thank you very much. Yeah.